Today's topic is on searching. So first we're going to look at different searching algorithms and different data structures that we use for searching. So after this, you should be able to list the options in implementing search functions. Okay, here's an overview. There are different algorithms. There's sequential search, binary search, and hash tables. And in binary search, there's iterative and recursive. With the sequential search, you could implement it with linked list or array of records. Binary search, you can implement it with array of records or with binary tree. And with hash tables, you can implement it with linked list or array of records. So let's go look at sequential search using array of records, which is the easiest one. So now we'll look at the algorithm for linear sequential search and using the data structure of array of records. So after this module, you should be able to implement this in C++. Okay. Back in the 80s, I was in Bedok Methodist Church, and Bedok Methodist Church had a church fair, and my friend Anthony had this idea that, oh, you know what, let's put the baptism records on his computer. And he had this Apple II computer, and so that at the church fair, each person could come up and look up their baptism date by just typing their name in the computer. Now, that was in the early 80s. It was an Apple II computer, and they were like, this is so high tech, because back then, like, no normal people had computers, or very few. And so it's like, wow, we have this high tech church. So Anthony had to figure out, okay, how to find a piece of data in a collection. And so the easiest way, which he thought of, he had no training yet because this is, he was just a teenager at the time, and is to start at the first piece and keep looking until you find it. So this is the Anthony's algorithm. He would search through the records, going one by one, and all the records were stored on this 5¼ inch diskette on this Apple II. And it was very slow and loud. When you search, you go and then search through the disk one by one. Now, this is a picture of an Apple II. Now, it's an old Apple II, and it's quite dusty, but Anthony's was pretty new at the time. So, since the records were in alphabetical order, if your name was like Ang Ah Beng, then it'd find it pretty quickly. It's like, okay, then you find the record. But what if your name was Zhang Jujin? It'll go, and you stand there for 5 minutes waiting for it to come up with the answer. And 5 minutes is a long time. You're just standing there waiting, right? So it was terrible. And that's because it's searching through one by one. And the disk access was so slow, and you're going through one by one, so it's check to see, is this name? Nope. Next name? Nope. And so it'll go through one by one and search through, and it took a long time. So we're going to show this. This is the algorithm that he used. Now, of course, it won't take 5 minutes because computers are much faster nowadays, and we're not using a floppy disk, and it's all in RAM, so it's much faster. But still, this is the algorithm that we are using. So we will use a sequential linear search, and the data structure is an array of records. So if these are your records, for example, if Ang Ah Beng, 25th December 1969, and then Ian Chai, 12 June 1989, J.D. White, 10 May 1967, and so on. Now, in a real record, you have a lot more people. Like, in like that church had like several hundred people at the time, and so it's a lot more records in the real example. So let's look at the code. Okay, here's the code. Firstly, you have just the standard headers, and then here we have a record that has the name of the parishioner and the date of the baptism. And you'll need to have something to read the data from the file, and then store it into this array, and the search, where it would take the key, which is the name of the person you're looking for, and the record array, and also how big is the array. So here's the main function. We have this result, which is the place in the array where the record is found, and we have this query, which is for people to type in the name. This is the number of actual records, and so we have this record baptism array of size MDIR, and the difference between MDIR and NDIR is MDIR is the maximum size of the records, whereas of the record array, whereas NDIR is the actual number of records that we read from the hard disk. Okay, and NDIR equals read data baptism, which is to read the data from the disk into memory, and then you input the parishioner's name, and it searches, and if it cannot find, then it says not found, but if it's found, then it prints the person's result. So for example, it says, if you search for Ian Chai, then it looks through the records and it finds Ian Chai's baptism was on 12 June 1989. Oh, by the way, this was not in Anthony's original database because obviously 1989 is not early 80s. Okay, so here's this function to read the data. So we open the file records.txt and we keep reading. First of all, we check to see did the file actually open properly. Then we keep reading until there's no more lines to get, or if the number of records is bigger than the number of space that we had reserved in our array. So we keep reading and read the name and date into the array, and finally we return the number of records read. So the search function here is, it has to have the name to look for, and then where to look, which is the array that we are looking in, and the size of the array. So we search through one by one. We check each element to see, is it matching the key that we're looking for? If it is, then we return. Otherwise, if we've gone through the whole array and we haven't found it, then we return -1 to indicate that it's not found.
We start with our main function. This is the array baptism for our sequential search demo. There are 4 records to our array. They are Ang Ah Beng, baptized in 69, Ian Chai, baptized in 89, J.D. White, baptized in 67, and Koo Kai Lee, baptized in 92. Now we declare 2 more variables. Result is an integer variable, while query is a character string. Suppose the user types Ian Chai for the name to search. This is stored in query. Now we call search. This causes key to point to the same place as query. Dir size gets a copy of the value of capital dir size, which is 4. We now make dir point to the same place as baptism. J is an integer variable. J has been initialized to 0, therefore J is less than dir size, which is 4. So we compare the name Ian Chai with the data in location J, which is 0, and find that Ang Ah Beng is not the same as Ian Chai. Because it is not a match, we increment J to 1. Therefore, J is still less than the dir size, which is 4. So we compare the name Ian Chai with the data in location J, which is 1, and find that Ian Chai is the same as Ian Chai. Because it is a match, search returns 1, and the 1 is put into the result. The result is not -1, therefore we print Ian Chai was baptized in 89. Suppose the user now types Kong for the name to search. This is stored in query. So we call search again in the same manner. j is an integer variable. J has been initialized to 0, therefore j is less than dir size, which is 4. So we compare the name Kong with the data in location j, which is 0, and find that Ang Ah Beng is not the same as Kong. Because it is not a match, we increment j to 1. Therefore, j is still less than the dir size, which is 4. So we compare the name Kong with the data in the location j, which is 1, and find that Ian Chai is not the same as Kong. Because it is not a match, we increment j to 2. Therefore, j is still less than the dir size, which is 4. So, we compare the name Kong with the data in location j, which is 2, and find that JD White is not the same as Kong. Because it is not a match, we increment j to 3. Therefore, j is still less than the dir size, which is 4. So, we compare the name Kong with the data in location j, which is 3, and find that Hu Kai Li is not the same as Kong. Because it is not a match, we increment j to 4. Therefore, j is not less than the dir size, which is 4. Because that is not a match at all, search returns -1, and the -1 is put into result. The result is -1. Therefore, we print not found.
So how long does sequential search take? Well, consider that what we have is it goes through one by one. So, if there are 10 things, then it's going to take 10 times at most. Like if the thing you're looking for is the last thing, it'll take 10 steps, right? If there's 100 things, then it's going to take 100 steps. If there's 1,000 things, then it takes 1,000 steps. So the amount of time it takes is linear according to how many things there are, right? So if the thing is n, the number of things is n, then it's going to take on the order of n times to finish the search. So when would I use this kind of simple algorithm? Since the sequential search is simple and the data does not need to be structured. It doesn't have to be in order. It can be in any random order. I just search through one by one until I find the thing I'm looking for. So it's useful when the data is constantly changing, like it's always things are coming in, going out, and if the data set is small, because if it's very big, then it'll take a long time, just like as we saw with Anthony. So there are other search algorithms that are faster, which we will learn after this. So are there other suitable data structures than just arrays? Well, yes, we could use linked lists because you can just follow the pointer to the next entry, and it's easy to add or delete nodes when you have a linked list because you can insert in anywhere along the list. So in summary, we have investigated searching using the linear sequential search algorithm and using the arrays of records data structure. We find that it takes linear time, so it's useful only for small data sets, and the code is easy to write, and also it may be useful for rapidly changing data sets because you don't need to maintain some sort of structure. Now let's look at the next thing, which is the same sequential search algorithm, but this time we're using linked lists. So we will look at the linear sequential search algorithm. We are using the data structure of linked lists instead of arrays. And at the end of it, you should be able to implement it in C++. So in this module, we're going to now implement Anthony's directory of baptismal records where a parishioner enters his name and his baptismal date is returned. And we will use the sequential linear search algorithm using a linked list instead of an array. So we use the same set of sample data as before. We noted that in a real data there will be a lot more records than these. And let's look at the code. So the top is the same, and here we find that we don't need to say how many records there are, unlike the earlier array version, because, well, a linked list can just grow until you run out of memory. So we do need a linked list, and this linked list contains the data and the pointer to the next node. So the data consists of name and date. So if you remember back in the linked list chapter, we just showed a data that was one thing, but here we have two things, but we still have that same structure of having a next node, a next pointer, the next pointer which points to the next node. And this should be familiar from the linked list, where you have init LL node, and then we have read data, which is new, but it's similar to the one in the array version. And then we have the search. So in the main body, we have to make, we have the read data build the linked list for us. We just have the pointers ready, and then we assign it to head. So as before, we ask the user to enter what they want to search for, then we call the search. And this time the search, instead of you tell it an array, you're telling it pointer to the linked list. And if the result is a null pointer, that means that we did not find it. Whereas if we did find it, then it would have result would have been a pointer to a particular baptism record. So we just print out the baptism record. So the output looks exactly the same as before. You type in the name to search, and then it shows you when that person was baptized. And we look at the init LL node and read data functions. Well, here, the init LL node function, this is very similar to what you had before in the init LL node in the linked list. The only difference is that now we are going to take this string and split it as a comma separated input into the name and the date. Then for the read data function, we will first make a head node, and then we say the current is at the head node, and we read from the file into the next node, into the next node, and so on until we run out of data, and we just return the head node. And the sequential search algorithm, we start with the key and the head of the linked list. So while I'm looking at, while the current is a node, so then I look at the current key. If the key is what we're looking for, then I return that and go to, otherwise I don't return, I go to the next node. Once I get to the end, that means the current will be a null pointer, then that means I didn't find it, so I return null pointer. So in summary, the implementation is invisible to the user. The output looks exactly the same to user. The function calls are very similar to that. And the code is slightly longer because we have to do this dynamic memory allocation rather than static memory allocation. But this allows us to add nodes in the middle somewhere, and we can remove nodes anywhere along the line easily. So that's what we saw as advantages of linked lists over arrays earlier. Okay, so now we've done the sequential search. Now let's look at binary search. Binary search first with arrays. So now we're going to look at binary search, and we're going to have two different versions, the recursive version and the iterative version. And we'll have doing it on an array of records. And so then you should know when this algorithm will be used and when this data structure should be used and how to implement it in C++. And we also figure out how long it takes. So big O is just saying how long it takes, the order of magnitude of time that it takes. Okay, so you remember Anthony, he couldn't have done anything about the slow floppy disk because that's what he had. Okay, but if he could have done a better search algorithm, he could have gone faster. So we can use binary search. He could have used binary search had he known about binary search. Remember, he was still in secondary school. He had not gone to computer science. He had not studied computer science yet at all at that time. So he didn't know about binary search. But if he knew about binary search, he could actually have speeded up things. So what is a binary search? Well, think about how you use a dictionary. Right? Okay, nowadays you guys probably use dictionary by just going online and searching. This example of telephone book is like, telephone book? What's a telephone book? Well, back when we wrote this book in the year 2001, or actually I think I wrote this example in 1999 maybe. telephone books were still something. That what it is that it's an alphabetical list of all the of all the people who had telephones and their phone numbers. So what you do when you have something like that is that you don't start on the first page and then search through looking for the name of the person you want, right? What you do is you kind of open it in the middle. Yeah, if you're looking for someone with Z, then you you take forever, one page at a time. So what you do is you open it in the middle and you see, is the name you're looking for on that page? If it is, then great. You have found it already and you just read the phone number. But if it's not there, then you see, is the name I'm looking for less than or greater than, in alphabetical order, the names on this page. So if less than, I look on the left side. If it's more than, I look on the right side. So again, we have the same data, and we're going to do it with binary search. So we will use recursion to split, because what happens is when you split half of it, then you just do the same thing as you did earlier, only with half of the records. So here's what we do. We have a record that has the name and the date, just like we did in the sequential search. And now we have to tell it the start and end. So in the sequential search, we didn't have this start and end, we just had the size of the array. Here, now we have the start, where in the array to start searching and where in the array to stop searching. And the main program is similar to the one in sequential search, except that you have to tell it the start and the end. The output looks exactly the same. You type in the name and then it tells you the baptismal date. Only thing is that it runs faster. So the read data is the same as the one for the sequential search array, so we won't discuss much of it, but we just go straight on to the search function where the interesting thing happens. So in a search function, you have the name to look for and the array you're looking for it in, but now you have the start and end index. So what we do is we look in the middle, just like when we did the telephone book, we opened it and we looked it in the middle and see, is the name we're looking for on the left or on the right. So if the name you're looking for is right here, then we return, we found it. But if I'm at the last page already, like split until it's already done, then you also return and you say, this time you say that I didn't find it. But if it's less than the current one, then I look on the left side. See, this is the start until the middle. And if it's more than the current one, then I look from the middle till the end. So it's on the right side. So the recursive case is keep looking, but you're only looking in half the amount. So eventually you run to the last page and you stop. So how do we start the binary search? Is just like before, except that you have, this part is the same, this part is the same, this part's different. You have to tell it the first element to search for and the last element to search for. And you're not telling it the number of elements like you did in the sequential search. So to visualize the program flow, we find a midpoint. If we found a match, then we say finished. If we didn't find a match, then we say do a recursive call on the first half. Or if it's less. If it's more, then we say do a recursive call on the second half. So this is the code. This blue part matches here. This one matches here. This one matches here. And this is this part here. Okay?
We start with our main function. This is the array baptism for our binary search demo. There are 4 records in our array. They are Ang Ah Beng, baptized in 69, Ian Chai, baptized in 89, J.D. White, baptized in 67, and Koo Kai Lee, baptized in 92. We now declare result as an integer variable and query as a character string. Suppose the user now types Ian Chai for the name to search. This is stored in query. Now we call bin search, which requires as input the index of the first and one after the last element of the array. Key points to the same place as query. Start gets 0, end gets dir size, which is 4. And dir points to the same place as baptism. Mid is equal to 0 plus 4 divided by 2, which is 2. So, we compare the name Ian Chai with the data in location mid, which is 2, and find that J.D. White is not the same as Ian Chai. The result shows that we should look in the first half. This means that in the new bin search, we have the same start, but the new end is mid. This means start gets 0, end gets 2. The new key and dir have the same values as in the first bin search. Mid is equal to 0 plus 2 divided by 2, which is 1. So we compare the name Ian Chai with the data in the location of mid, which is 1, and find that Ian Chai is the same as Ian Chai. The second bin search returns mid, which is 1, to the first bin search. The first bin search returns that 1, and that 1 is put into result. The result is not minus 1. Therefore, we print Ian Chai's grade is 22. Suppose the user now types Kong for the name to search. This is stored in query. So, we call bin search again in the same manner. Mid is equals to 0 plus 4 and divided by 2, which is 2. So we compare the name Kong with the data in location mid, that is 2, and find that J.D. White is not the same as Kong. The result indicates that we should search the second half. This means that the new start is going to be mid, and the new end is the same as the old end. That is to say, start gets 2 and end gets 4. In the second bin search, the new key and dir have the same values as in the first bin search. Mid is equals to 2 plus 4 divided by 2, which is 3. So we compare the name Kong with the data in location mid, which is 3, and find that Ku Kai Lee is not the same as Kong. The result indicates that we should search the first half. This means that we pass the same start but a new end, the new end being mid. The start gets 2 and the end gets 3. Key and dir once again stays exactly the same. This means, however, that the new start, which is 2, after adding 1 is equals to 3, which is equal to the value of the new end. Therefore, the third bin search returns negative 1 to the second bin search. The second bin search returns that negative 1 to the first bin search. And the first bin search returns that negative 1 to the main, which puts it into result. The result is negative 1. Therefore, we print not found.
This is a VP diagram animation of binary search using arrays. We start by calling the binary search function with the indices of the first and last position in the array of records to search in, because we want it to search the whole array. Now, in the search function, we are going to search from position 0 till position 7. So we find the middle, which is 3. We do the comparison of the key with the item at the middle. It's not the one we're looking for, so we don't return. Start and end haven't crossed yet, so we don't return. The result is less than 0. So we recursively call search on the first half of the array. Now the yellow search has called the blue search. which is searching from 0 to 2. The middle is 1. We do the comparison of the key with the item at the middle. The search result matches. So we return from the blue search to the yellow search, which then returns the location found to main. So now main has the location of the item we are searching for.
Alright, now let's take a look at how long this will take. How long it takes is dominated by the comparison of the strings, and so the worst possible time is if you can't find the person in the database. So we look at what happens if you can't find someone in the database. Each time it does this recursive call here, the recursive call is here, this one, search. It's going to split it in half, okay? When either it goes this way or this way. So if we can't find the person in the database, then it's going to each time split in half, and that means the array is going to half each time. So that means that the worst case is you go all the way and you find the last one and you say, okay, we cannot find it. So that would be log base 2 of n. So that means that it's proportional to log base 2 of the number of things in the database. Okay, what would have been the effect of implementing Anthony's program with binary search? So instead of having it go from the number of people in the database, or it goes to log base 2 of it. So for example, if you're looking for Zhang Zhujin in a database of 256 people, and let's say it takes 1 second for that old Apple II to check each record, linear search would take 4 minutes and 16 seconds for Zhang Zhujin. So of course, it'd be faster just to look through the books if you're going to do that. But if Anthony had used binary search, then after the first second, it would have gone down to 128 records. Then the second it would have 64 records. The third second, it would have 32 records. Fourth second is 16. Fifth second, it's 8. 6th second is 4, and 7th second is 2. So we would have found it in 8 seconds. All right, we would have had his answer in 8 seconds. So that's much faster than 4 minutes 16 seconds. So you can see the advantage of doing binary search. So the binary search still takes 8 seconds, but the linear search would take, a linear search, if we were looking for Ang Ah Beng instead, it would only still take 1 second for Ang Ah Beng because he's the first person. So you look at the first person and you already got Ang Ah Beng. But if you're doing binary search with Ang Ah Beng, it would still take 8 seconds because it would still have to split and get down to it. What happens in 1 second is the person who's right in the middle, then it would take 1 second. Okay, now can we rewrite the binary search iterative? And the answer is yes. This particular case, to replace the recursion with a while loop, is quite simple. So what we do is here, instead of having a recursive call, we just say the middle, okay, we have this while loop. We check to see if it is if it is here, the middle starts from we go to the middle and then we check, is it the one before or after? If it is before, then we change the end to be just below the middle. If it's the one after, then we change the end to the one, we change the start, to the one just after the middle. So for example, if you had an array that's going from here to here, right? And we find the middle here. So the start is here and end is here, right? And the middle is here. So we say change the start. Let's say the thing I'm looking for is on the left side. Then we say change the start, change the end to be the middle minus 1. So be looking at this side. If it's bigger, then we change the start from here to the middle plus 1. So you'll be looking on this side. This doesn't make any difference to the calling program because the function still gives the same answer on the outside. Can we use other data structures? Well, yes. We could use binary trees. And this is in fact a natural data structure to use for binary search. And it's especially good when the data can change, because in an array in an array method, then you have to keep reordering the data, looking for where to put it in. Okay, so now we have investigated searching using binary search, both in the recursion and iterative method. And we look at the data structure of using array of records, and we've figured out how long it takes, which is on the order of log n. So it's useful for large data sets. It's much faster than doing a sequential search on average. And we use the data structure of array of records for a constant sorted data set, but we can also look at binary trees for changing data sets. Okay, so let's look at the binary search tree for changing data sets. Okay, so now we're going to look at the algorithm for binary tree. The data structure is tree, and after this module, you should be able to explain why binary trees are useful in searching and implement this algorithm in C++. Okay. Now, what happens if, well, I mean, in the previous example for the binary search, we had the data already in alphabetical order. However, a lot of times your data comes not in alphabetical order, like for example like this. Binary search is much faster than sequential search only if the data is already ordered. If it's not already ordered, then you must first sort it to make it in order. And as you will learn later when we get to the sorting algorithms, the faster sorts take the order of n log n. And so a sequential search using a linked list can add more data, but the search will be O of n. While binary search can do this log n, but insertions will be O of n, as we have to copy items to make space. So binary search trees to the rescue. It's kind of a compromise to try and achieve the best for both worlds, because binary trees is where every node contains a key, and when you insert the next child, if it exists, it's going to be less than the key of the parent, and the right child will be more than the key of the parent. So here's an example. See, L, low, Ian is less than low. Ong is more than low, right, in alphabetical order. Ang is less than Ian. JD is bigger than Ian. Mark is less than Ong. Rachel is more than Ong. So when we do an in-order traversal, we actually get the nodes in ascending order. So here are the functions that we need to get that kind of tree. To deal with that kind of tree, we need to be able to search for a record in the tree. We need to be able to add records to the search tree, delete the records from the search tree, and keep the tree approximately balanced. That one's optional, but we'll talk about that later. And our code here does the first tree, doesn't keep it balanced. So this module's code will implement the Anthony's directory of baptismal records, where a parishioner enters his name and his baptismal date is returned. And we will use the algorithm binary search. The data structure, we're going to use a tree. So let's look at the code here. Firstly, we're going to define these function return values because it's a good practice to define the constants and not just use the numbers. Then you know what it means. It means like -1 we mean less than, equal means 0, +1 is more than, and then found is 1 and not found is 0, and deleted is -1. Okay. Then here we find that the definitions and prototypes are similar to the ones in earlier binary trees, but we just have to add this relevant data of name and date. And this init bin tree node also is similar, just add name and date. But then we have all these new function prototypes: compare, node, data, insert, binary search tree, binary, and then the search for the the tree and then delete binary search tree and delete child. Okay, the main is actually the same main as in the sequential search with the linked list. The read data, we will read from this rec2.txt, which is the unordered data, and we first make the root to be null. Then we check to see if the file is open properly. If it is, then we read the next line and we get the name and date from that line, and we call init bin_tree node if we are at a new tree. Otherwise, we call insert bst. Okay, and init bin_tree node is just exactly the same as the bin_tree init bin_tree node from the earlier binary tree init, except that we just put our data fields name and date rather than the old data. Visit is just the same, it's just to print the name, and in order is the same as before. Now, here we have compare node data. That means it's going to tell us whether x is less than y, or is the same as y, or is greater than y. So we use the compare function and return equal if it's the same, and return less if it's less, and return more if it's more. And the reason we use this compare node data is that it makes it easier to change the node's data type. Here we have the insert binary search tree. And here, this part here, we check to see if the current node is less or more than the current key. What we are trying to insert, is it more or less than the current key? If it's less, then we check to see that if there's a space, then we add it to a new node. Otherwise, we continue recursive calls. So less, then we're going to go to the left. Right, we're going to go to the, if more, then we go to the right. And otherwise, we will just, this is what to do if an item already exists with the same key. Here, we don't do anything because we just say, okay, it's the same, and we don't have to insert it. But a possible alternative is, instead of just not doing anything, you could say update the date. Perhaps the date is different. So in effect, adding the same person is to update the baptism date. And this is the search. You return the address of the node containing the required key if it exists. Otherwise, it returns null pointer. So what we do is we check to see is the thing we're looking for, the name we're looking for, is it the same as the current node's name? If it's less, then we search to the left. If it's more, then we search to the right. If it's the same, then we return the current node. If we've gone through all and we haven't found it, then we return null pointer. And then we have this function to delete a node, which we don't use in this example program, but it's maybe used in some other programs, where you compare the key with the current node's key, and if it's equal, we return found. If it's not equal, then we recurse on the correct child, meaning that if it's not equal, then if it's less, then we go to the left. If it's more, then we go to the right. And when we find it, we call delete child. And delete child makes the deletion by repositioning the pointers and free the memory. So here we have the delete BST. So if the node is the current node, if the current node is not null, because if it's null, then it means it's not found. Then we see, is the current node the same? Okay, if it's the same, we return found. If it's left, then we search on the left. If it's more, then we search on the right. Then here's the delete child. Here we use the pointer to hold the address of the child to delete. And this is, when we test this, that means that there's no children, so we mark it for deletion. Here it's if you have one child, so we mark the grandchild to replace the child. And if it's two children, then you mark the left grandchild to replace the child. And you look for the place to put the right grandchild in the tree. And then you free the memory occupied by the delete child. And you replace the parent's node reference with the child of the child with the one of the grandchild. So you essentially move the tree up. So the output looks exactly the same again. You search for the person, you get the person's baptismal date. But let's look at how the data is structured in memory. So here the root, at first you insert one node and it looks like this. Then if you insert Ian Chai, then it's going to say, oh, Ian Chai is less than low poly. So you'll put it on the left side. Then when you insert Ong Hui Yi, you see that Ong is greater than low, so it puts on the right side. And then when you insert JD White, you compare with low, it's less, so you go compare with, so you go to the left. Then you compare J with I, and it's more, so you go to the right. So it puts it on the right side. So how do I search for the data? It's implemented in the FindBST. We start at the root node, which is the baptism pointer, and see if the data matches. If it's the same thing, that means we found it. If it's less or greater, if we haven't found it, that means it's less or greater. If it's less, we go to the left and search again recursively. If it's more, then we go to the right and search again recursively. And if it's null pointer, then it means that we have not found, it's not in the tree. Okay, the thing you're looking for is not in the tree. How do I insert new data? As we implemented in the insert BST, we search for the item, but instead of reporting that it's not found, we insert it into the location where it should go. And how do I delete data? As implemented in the delete BST, we search for the data. If the data is not found, then we give the error saying you can't delete something that's not there. If the data is found, then if the children are null, okay, let's say you found Tiru, you want to delete Tiru. If the children are null, then simply null it, okay, and then you free that node. So Tiru is removed. But if you are wanting to remove low, for example, then you can't just delete it, because then you lose this stuff, right? So what you have to do is you have to promote JD to become the right child of Bao. Okay, so you see, instead of Bao goes to low and then goes to JD, low is removed and Bao goes straight to JD. And how about if there are two children? Then you have to pick one child to replace the node. If you pick the left child, then JD will become the new head node, the root of this thing. Then we have to insert this one in the correct place in the JD tree. So you have to take the Tiru and go down, JD to the left, and then Tiru is bigger than J, so it's going to go down here. T is still bigger than K, so it'll go down here. So you see, that's why it ends up here. However, if you do it the other way and you do the right child, then it's just the same thing, just with the left and right exchanged. Okay, why is delete BST not called in the ExamPro program? It's simply because this application doesn't require it, because baptismal records will never be deleted, just as birth records are not deleted. But we still showed you how to do the delete, because there are many applications where you do need to delete. So is there any danger in using a binary search tree? Yes, because a tree can become unbalanced. For example, if your record text is already sorted, then all the children will be right nodes, and so you just go down all on the right side, and it degenerates into a linked list. And the way you fix that is you balance the tree. But balancing the tree is not that straightforward. You first need to decide, is it worth the cost? Because if you have a random distribution, then 39% more than a balanced tree, it's going to be it'll cost 39% more than balanced tree. And in many cases, it's not. So in other situations, savings could be significant. For example, when there are a lot more searches than insertions. So if you want to learn how to balance a tree, you would have to implement an AVL search tree, and I give you a link here that you can explore and learn how to balance a tree if you want to do it. So in summary, a binary search tree is a compromise between the growability of a linked list and the speed of a binary search. And in-order traversal actually gives us an ordered list. And how long it takes is proportional to the log of the number of things in the tree if the tree is balanced. So if it's not balanced, it degenerates into proportional to the number of things. So it becomes a sequential search. Okay, so that was binary search. Now we have hash tables. So now we'll investigate searching with hash tables, and we're going to use arrays for this. And after this module, you should be able to implement this algorithm using C++. Why do we bother with hash tables? Well, you remember sequential search, the speed is about proportional to the number of items. And binary search, the speed is about proportional to the log of the number of items. Hash tables, it's always just takes the same amount of time. Well, in the ideal case, okay? And if your hash table is not full, it takes just one. That means that it takes the same amount of time no matter how many things are in your hash table, as long as the hash table is not full. So how do we do a hash table? First, you need to convert the key into an integer. For example, the parishioner's name or any other data in the record to be stored needs to be converted into an integer, and the integer size is practical for a table size. So, which means that if the integer size is like 10 billion and it's not practical for a table size. It depends on how much memory you have, of course. But if the integer size is like 1,000, then okay, fine. On a normal PC, you can fit that. And the function can be as simple or as complicated as necessary to make that to get it to work. So in this module's code, we convert the parishioner's name into an integer and store the information in an array and allow the user to search for the baptismal date by the parishioner's name. So we're going to use the same sample data here. And here is the code for this hash function. Here we have this m hash, which is the size of a hash table, and it should be a prime number approximately 4 times the number of the records. So first thing you notice that, oh, hash table, you're required to make your array much bigger than the number of records you expect to have, and about 4 times the number of records you expect to have. And the read data is the same as the sequential search read data. And then you have this special hash function, which is to convert the key into an array index. And then you have this prepare hash table function, which uses the hash function to reference each entry from the hash table. And then you have the search, which takes, in addition to the key and into the records, you also have to have the hash table. Okay, and here we have the main function of the hash table. The main is just like the one for the sequential search, except for a couple of things here. Firstly, we have to have this hash table, and then we have to have this call to create the hash table, and then after that, you have to give the hash table to the search as well. Otherwise, the rest of this main function is the same as the one for sequential search. Now let's look at the hash function. The hash function's purpose is to convert the name of the parishioner into an integer between 0 and m hash. Okay, or the name of the key, whatever your key is. In this case, it's the name of the parishioner. And here we sum up the total of all the characters in the name, and then we modulo it with m hash, and that will give us a hash function, a hash number, that integer that is between 0 and m hash. So this is a very simple hash function. We just add up all the values of the characters in the name, and then we modulo m hash. And we prepare a hash table array to link to the hash value of the table of the actual index of that person by using this prepare hash table function. And what it does is that you go through, you get the index you calculate the hash function of the name, and that gives us the index, and then we put in the hash function that name, the location in the original array of the name. Then here's how this search works. We have the hash of, we get the hash of the name of the parishioner. Then from the hash table, we find the record where this parishioner should be located by calling the hash table function, looking up in the hash table. And then we check to see if the matching array element is there. And if it is, we return the index. If it's not, then we return not found. So just like before, to the user it looks the same, it just works faster. Okay, what is the general flow of the program? Well, first we have to read the data from the file into an array of records, and then we need to create the hash table using the hash function of the ASCII values of characters in the name. And then we need to do the mod and get the number between 0 and m hash, the site which tells us where in the hash table to look. And then we access the individual record by using the hash function and look up in the hash table, and we directly access the record immediately. So that's why it takes the same amount of time no matter how many things there are. That is providing there is no collision, and by collision we mean that two different keys map to the same location. Okay, that's that proviso there. So the steps involved in building a hash table, we have the elements stored at the index. Like here we have Ang at 0 and Ian at 1 and Hu at 2 and Zhang at 3. Then we do the hash function, which will tell us then in the hash table where to look up things. So the hash function, when we're looking to access an individual record, we put that in the hash function and we can find, oh, it's in position 1 immediately in the hash table. So that's providing that we don't have collisions, okay? So in this simple program, we didn't deal with the collisions, but are there other types of hash functions? Yes, there are many. There's the simple one where the index is the key, but that's not practical in most cases as you run out of space, because the index is, then you would have to have as many as many things in your array as there's the possibility of the hash function result. And then the truncation is the index is the last digit of the key. There's folding, which is combining into parts. You partition the parts and combine by adding or multiplying. And the one that we used, which is the modular arithmetic, where you take the key and then you mod by the m hash. And it's usually good for the m hash to be a prime number to avoid collisions. So what do we do when two keys map to one index? That's what we meant by collision earlier. For example, if we had a person named Nai Chai and you have Ian Chai, and we use our function which was just add up all the letters, right? Then we would end up mapping to the same index, and we would have to resolve the collision. And so we will discuss later how we resolve this collision. And remember, a collision occurs when two different keys, when given to a hash function, produce the same index. Okay, well, collisions will slow you down, so we want to minimize collisions. So a good size for an array to minimize collision has to be found, and because hashing is only effective if the table is not too full. If it's too full, then you get lots of collisions, and it degenerates into a linear search. So more complex implementations usually just reallocate into a bigger array when it's too full. But if you don't have a memory problem, then the rule of thumb is to make the array size a prime number approximately 4 times the amount of data you expect. So when would you use a hash function rather than a sequential or binary search? If your keys are sparsely distributed, so for example, if you have 200 students and the student IDs are 10-digit long, and if a student ID number is consecutive, starting from 1 to 255, then it's probably not worth the effort. You can just use a normal array. But you want to use hash tables when speed is a prime concern, and there's enough memory to store the hash table. Because the whole thing about hash table is it's very fast, right? So, but it uses a lot of memory to do it. Okay. So we mentioned about collisions earlier, that the problem is that when you hash to the same location. So we must resolve those collisions, because eventually you will always get collisions. And so we must resolve them, and there are 3 main methods to resolve collisions, which is One is replacement, which means that you just put the new thing in where the old thing was. Well, that's not a good idea usually because you don't want to lose your data. So another way is to use open addressing to put it somewhere else. That means that it hashes to here, but that's not what we want, so we look further until we find a blank space and put it there. The other one is chaining, is to make a linked list. That means that each bucket is not one item, it's actually the head of a linked list of items. So if it cannot fit here, then you put a linked list of the items and the next ones and next one. So then you can make the linked list longer as necessary. Okay, open addressing, there's two methods of doing it. Well, actually more than two, but there are two main ones. One is linear probing. Okay, where do we want to put the other thing is you start at the point of collision and do a sequential search for an empty location and put it there. If it reaches the end of the table, you go back to the beginning. And the problem with this, it has a tendency towards clustering. That means a whole bunch of things get stuck together, so you have to do a linear search on there. Quadratic probing tends to reduce clustering. You go first h plus 1, then h plus 4, then h plus 9, then h plus 16, and so on. That means it's 1 squared, 2 squared, 3 squared, 4 squared, okay? 5 squared, 6 squared, and so on. So here's an example of linear probing. First step, the first one, we hash 12 in, it becomes 5. Okay, so it goes, 12 goes into 5. Second one, we hash 15, it becomes 1. So we put 15 at 1. Then third one, we hash 21, it becomes 0, so we put 21 here. Then we hash 36, it becomes 1. Well, 1 already has something there. So we do linear probing and we go to the next blank place, we put it there. Then 84, we hash it to 0. So again, there's already something there. So we look at the next blank space, there's something there. So we look at the next blank space, there's something there. So we find this blank space and we put it there. And then 96 hashes to 5. We find 12 is already there, so we put 96 in the next place. So this is what we mean by linear probing. So you see that if I'm looking for 84, I'm not having to do a linear search all from here, 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 here until I find it. Okay, then another way to do it is resolving collisions by chaining. We insert the 12 here, then we insert 15 here, then we insert 21 here, then we want to insert 36 here, but there's 15 there already, so we make a linked list and we just put 36 also in the same box by using a linked list. And then we add the 84 and there's something there already, so we add the 84 as a linked list in there. And then we add the 96 and the 12 there, so we just add it as a linked list there. So now here it's much less searching. See, you only search one, you just have to search at most 2 items in this example. Whereas in this example, you had to search 4 items. Okay? So the summary of hashing is we are trying to get the same speed no matter how many things. It only works to get that kind of speed when the table is not full. So the rule of thumb is that the hash table needs to be 4 times the size of the data. The hash function turns the key into an index of the table. And from the table, we get index of entry in the database. And we will get collisions sooner or later, so we need to resolve the collisions. The bad one is replacement. Open addressing is another way, and probably the best one is chaining. Okay, so in summary, we have looked at the different choices of algorithms, the different choices of data structures. And so now we want you to be able to list the options in implementing search functions. And under a given set of conditions, determine the algorithm and structure to use the data to use. So remember this diagram from the beginning of our lecture. Different ways to do searching. We can do sequential search, and sequential search can be done using a simple linked list or an array of records. We can do binary search, which we can do either iteratively or recursively. and it can use an array of records or a binary tree. And we can use hash, which we can do using array of records, or you could also use a linked list. So the key points are the task of searching. There are many possible algorithms and different ways to implement the algorithm. And each algorithm can have different data structures you use, but not all data structures can be used with every algorithm because of just the nature of the things. And searching is not an exception. For most tasks, we have choices. So how do we select the searching method? If you have a small size, you could use sequential search with arrays or sequential search with linked lists. If you have a large size, you probably want to use binary search either with arrays or with trees. So size is one of the considerations. The size tells you what algorithm you use. The mutability tells you what data structure to use, because arrays are not very mutable, right? You can't change them very easily. Whereas linked lists, linked lists and trees, you can change them. But before we can use binary search, we must sort the data. So in the next lesson, we will look at how to sort the data. That is, if we use a binary search that is not using trees. Okay, so that's the end of today's lesson.